Hi, Assalamualaikum and good day to all students. For this video, we are going to cover for chapter 6 heat transfer in FST209. Alright, so please be ready with your lecture notes together with your pen because throughout this video, I will draw some diagrams or equations or calculation on the screen so that you will have a better understanding for this particular chapter. Alright, so now let's move on to the introduction of heat transfer in chapter 6. Alright, for heat transfer, this one is one of the important unit operation in any of food industry because it related with the refrigeration or freezing or thermal sterilization, and it also involved with the drying of the food material together with the evaporation of the moisture from the food product. And this particular heat transfer, it involves when the process requiring for heating or cooling processes. And this particular heat transfer is important because this one can be used in order to slow down the microbial growth or to destroy the pathogenic microorganism, as well as to slow down the enzymatic degradation. Okay, so this particular heat transfer also may achieve to maintain or to enhance the desired sensorial properties. So for example, in terms of the color, the texture, and the flavor of the food product. Alright, so for the nature of heat flow, basically we have three method or three techniques of how the heat is being transferred. The first one is by using conduction, and then we have convection followed by radiation. Okay, so what is heat transfer? Heat transfer is a dynamic process in which heat is being transferred spontaneously from one body to another cooler body, meaning that the heat is being transferred from one hotter body to another cooler body. And basically the temperature, the heat transfer will always occur directional, meaning that one direction, it starts from the hot to cold temperature. Temperature difference and the resistance to heat flow will affect the rate of heat transfer. Resistance to heat flow meaning that probably the material of the equipment is having a resistance for the heat flow, so that one will affect of the rate of heat transfer, meaning that it requires a longer period of time to increase or to lower the temperature of the material. Okay, for the mechanism of heat transfer, the first one is by conduction. This one, it is a process of transfer for heat from one object to another object without any movement, meaning that the object is static, okay, without any movement of that particular object. Molecular energy is directly exchanged from hotter area to cooler area. So for example, if let's say you have refrigerator in your house, do you notice that at the back of the refrigerator is hot? Okay, so if you notice as well, at the back of the refrigerator, there is like a hook that is preventing from the refrigerator to be keep directly on the wall. Okay, the refrigerator needs to be allowed to have a space in between the refrigerator, at the back of the refrigerator, as well as to the surface of the wall. Okay, and this particular hook preventing from the refrigerator to be lean directly on the wall. Okay, why is that so? It's because this particular area, this empty space between the back of the refrigerator and the wall, is to allow for the heat to be transferred from the refrigerator, whereby the heat is being generated by the refrigerator, and it's supposed to be allowed for this particular heat to the environment, okay, to allow the transfer of the heat from the wall of the refrigerator to the environment. So that's why the refrigerator should not be leaned directly on the wall when it is in operation. Okay, and then the second nature of heat flow is by convection. For this particular convection, we have two types of convection. One is natural convection and the other one is forced convection. For convection, it is the transfer of heat from one portion of fluid or gas to another portion through the mixing among them. Okay, for natural convection, this type of convection, basically it naturally happen due to difference of density. For example, when you are boiling water. So for boiling water, the coil is basically located at the bottom of the kettle. Alright, so when the temperature increase because of the heat generated by the coil, so the water at the bottom will start to move up, okay, because the density of hot water is lesser compared to cold water. So that's why the hot water will move up and then the cold water at the surface will move down. And this particular rotational happen until all the temperature of the water achieve at boiling temperature. Alright. Okay, and then for the second convection method is by forced convection. This type of convection will happen due to the force that is given to the fluid or gas by using fan or pump. For example, when you go to any large store, and you can find that certain chiller area, their chiller area is being equipped with a fan that is situated at the top part of the chiller area, because this particular fan is used to force the cold air to go down and in order to maintain the cold temperature at that particular area. So that one is known as forced convection. Okay, and then the third method of nature of heat flow is by radiation, whereby the heat energy is being transferred by electromagnetic waves. Hot object will give heat in the form of radiation towards all direction. Okay, so it is a not one direction, meaning that if let's say we have one area like this, alright, and then the radiation will be passing to the food product, and it will start to channel out from every direction. Okay. Some of the radiation energy will be absorbed by the materials, some of them are going to be reflected. So it really depends on the capacity of the food to absorb or to reflect of the radiation energy. Okay, now let's move on with the heat conduction. For heat conduction, it is according to the Fourier's law. For Fourier's law, the sharpest slope of temperature during heat of transfer in particular object will become more heat resistant for that particular object. The thermal conductivity of the object is defined as quantity at its joule of heat flow for per square area through 1 meter thickness of the object and per unit difference in temperature for one particular unit of time. Okay, the unit is in second. So can you see here that the unit are all in SI unit? We use joule, and then we have area is in meter, and then the thickness also in meter, and then in terms of the temperature is in degrees Celsius, as well as time is in seconds. Okay, so when we have this, okay, so according to Fourier's law, then we have the equation of Q equals to Ka delta T over X. Alright, if you rewrite this one, it will become Q equals to Ka delta T over X. Alright? Okay, so the Q is a rate of heat transfer, right? Rate of heat transfer, meaning that this one is joule per second or watt. Okay, for Q, this one is either joule per second or it is in watt. Okay, and then delta T is temperature difference between one side versus another side. X is the thickness in meter. Can you see this one in meter? K is thermal conductivity of the object. Okay, A is the cross-section area measured perpendicularly to the direction of the heat flow. So basically the heat will flow from high temperature, okay, T1, it will flow to T2, whereby basically T1 normally the temperature is higher degree C than this temperature of T2, lower degree C. So for this delta T is temperature difference. Alright, for temperature difference, it can be in degree Celsius or Kelvin. Okay, remember I have mentioned to you before, whereby temperature difference of degree Celsius is at the same value of delta T in Kelvin. Okay, the unit in Kelvin and degree Celsius. Okay, remember I've mentioned before, for example, I have 10 degrees Celsius minus by 0 degrees Celsius. Okay, so the delta T I will get as 10 degrees Celsius. Okay, for Kelvin, for example, Kelvin, this one I write here. Okay, by using the same value of degree Celsius, we convert to Kelvin. Okay, for 10 degrees Celsius, what is the value in Kelvin? Alright, so for 10 degrees Celsius in Kelvin is 283.15 Kelvin. Okay, minus by for 0 Kelvin, what is the value for 0 Kelvin? In degree Celsius, sorry, from degree Celsius, 0 degree Celsius in Kelvin, after you convert, it becomes 273.15. Oh, this one is not, this one is supposed to be Kelvin. Okay, this one also should be Kelvin. So for the delta T, you will get delta T still as 10 Kelvin, except for the unit is different. This one is Kelvin, this one is degree Celsius. But the value for temperature difference is still 10. Okay, degree Celsius is 10, Kelvin also is 10. Alright, this one is delta T. Do you get that? Okay. So for example, one face of stainless steel plate, one face meaning that at one side, okay, one face is one side of stainless steel plate whereby it has the thickness is 1 cm, and this particular thickness is denoted by X, is maintained at 110 degrees Celsius while the other face is at 90 degrees Celsius. Assuming steady state condition, calculate the rate of heat transfer per unit area, this one is per unit area, through the plate. Thermal conductivity of stainless steel plate is 17 watt per meter degree Celsius. Assume the area is 1 meter square. So this one is A. Okay, so this one is T1, 110 degrees Celsius. 90 degrees Celsius, this one is T2. Okay, so what is the equation that you need to use in order for you to solve this particular problem? Okay, so first thing first, what you need to do is, as I mentioned before, gather all the information that you can get from the problem statement. Alright, so for thickness, it's been given in centimeter. This one, can you see it is in centimeter? So please convert to meter. Centimeter, you need to convert to meter. Alright, so for 1 cm, it is equivalent to 0.01 meter. How do I get this? 100 centimeter is equivalent to 1 meter. Okay, 100 centimeter is equivalent to 1 meter. So that's why for 1 centimeter, we will get 0.01 meter. So my advice, when you want to gather the information from the problem statement, immediately convert the unit into the unit that we are going to use. For example, this centimeter. We are not going to use this centimeter at the end of the final unit. We are going to use meter. So immediately, when you want to gather, immediately convert the unit to meter. Okay? And then, if let's say this particular temperature is given in Kelvin, do you need to convert the temperature in Kelvin? For example, the final unit you're supposed to express as watt per meter Kelvin. Oh, sorry. For example, you need to write as watt per meter Kelvin. So for this one, okay, so if let's say the thermal conductivity is given as K17 watt per meter Kelvin, do you need to convert this temperature? The temperature given in the problem statement is degree Celsius, but do you need to convert the temperature, this particular temperature? Because for this particular chapter, we are going to calculate for delta T. Okay, we are going to calculate for delta T. So if let's say delta T is T1 minus by T2, okay, if let's say we are calculating in degree Celsius, 110 minus by 90 degrees Celsius, right? So this one has become 20 degrees Celsius. But if let's say you convert this value 110 degrees Celsius to become Kelvin, 90 you convert also 90 degrees to Kelvin temperature, at the end you still will get 20. The temperature difference you will still get as 20. So it is not necessary for you to convert the temperature when you need to calculate for temperature difference. Okay? You need to hear this one properly. You do not need to calculate temperature difference if let's say the temperature is between degree Celsius to Kelvin. However, if let's say the temperature is given in degree Fahrenheit, then you need to convert the temperature because degree Fahrenheit is not SI unit. SI unit for temperature is only Kelvin and degree Celsius. And the value of temperature difference between degree Celsius and Kelvin are at the same value. Okay, do you get that? Alright, so now temperature at one phase is T1, 110 degrees Celsius. Okay, this one is coming from the problem statement. On the other phase, on the other side, one side is 110 and the other side is 90 degrees Celsius. Given K, thermal conductivity of stainless steel is 17 watt per meter degree Celsius. Every material, they have their own thermal conductivity. When we talk about stainless steel, they have their own specific conductivity, thermal conductivity. When we talk about wood, they have their own thermal conductivity. So they are different. So that's why you need to know how to properly use this particular equation and how to calculate. Okay? So we use the equation of Q equals to Ka delta T over X. It doesn't matter whether you want to per the X, whether you want to per the, throughout this equation, or you just want to per under delta T or under delta A, it will give you the same answer. Alright, so Q equals to Ka delta T over X, or you can write as like this, Q equals to Ka delta T over X. Alright, and plug in all the information given from the problem statement. Okay, so K, it is known, K is 17. Area is given already, this one, 1 meter square. And then delta T, calculate T1 minus by T2, starting from 110. Always starts from higher temperature to lower temperature. Alright, and then divide by the thickness. Okay, thickness, this one we already convert from centimeter to become meter. Okay, so the final answer after we have cancel out the unit, for example, this 1 degree Celsius, we set cancel with degree Celsius, and then for this particular meter we can cancel out for both meter and meter. So it only leaves with watt. So the answer is 34,000 watt. Alright, this one is a very simple example, and basically for this particular type of example, I will just give around 2 marks for this type of problem statement. Okay, now let's move on to heat transfer by conduction through cylinder and composite wall. Okay, so just now in previous example, this one we talk about one single material. Alright? For the next one, next slide, this one we are going to talk about the heat transfer by conduction through cylinder, because cylinder it requires the calculation of the area for the cylinder, and composite wall. Composite wall meaning that the wall is composed of several material. Maybe it is composed of 2 or 3 materials. Alright? So we are going to look one by one. Now we are going to look for the cylinder first. Heat transfer by conduction through cylinder. Okay, you need to make sure that you memorize these particular terms. Okay, because these particular terms will be heavily used in the calculation for the heat transfer by conduction through cylinder. Alright, this one is slide number 7. Okay, so for tube heat exchanger, when we are dealing with tube heat exchanger, tubing is cylinder. So you need to know the terms. The first term is inner heat transfer coefficient. Inner heat transfer coefficient is denoted as H, Hi. I, this one meaning for inner. Okay, I is inner. And the unit is watt per meter square Kelvin. Okay, watt per meter square Kelvin. Alright, and then the second term is outer heat transfer coefficient. H naught. H naught. This particular O, this one representing for outer. Okay, I inner, H naught is outer. You need to be careful with these two terms, because most of the students, they will interchangeably these particular terms, okay, Hi and H naught. Alright, and then the third one is thermal conductivity of tube wall. Thermal conductivity is K. Okay, K, the unit is watt per meter Kelvin, whereby inner heat transfer coefficient, can you see that this particular watt per meter square? Okay, this one is meter square. For Hi, H naught is meter square. But for K is only meter per meter. Okay, please take note that one, those units. Alright, and then diameter of the tube is Di. Di is the inner. Again, I is the inner. When you are being given diameter, can you calculate the radius? Okay, do you know that the difference between between the diameter and radius? For example, I have this circle. Okay, I have this circle, and from center, from here to here, this one is diameter. Okay, but when you cut it into half, from the center, halfway to the outer part, this one is radius. Alright, clear on that? Okay, so diameter is in meter. Alright, please make sure that you be careful with the unit. Diameter is in meter, and the inner radius, Ri, again, I is meant for inner. The unit is in meter as well. Okay, and then the thickness of the tube, X, is in meter, followed by outer radius, R naught, is in meter. Okay, how to calculate this R naught? R naught equals to Ri, the inner diameter, plus with X, the thickness. Okay, for example, I show you here. For example, I have a tubing. Okay, and this particular tubing, it has 2 layers. From the center to the outer part of this inner tube, this one is Ri. Okay, between these two tubes, alright, this one is X. Okay, and then from the center directly to the outer part, okay, this one is R naught. So that's why when you want to calculate for R naught equals to Ri plus X. Right? Because it starts from the center part to the inner part of the tubing, this one is Ri. And in between these two tubing, this one is the thickness of the tube. Okay, thickness is being denoted by X. So starting from the center to the outer part layer of the tubing, this one is R naught. So how to calculate R naught? R naught equals to Ri plus X. Right, so that's why you get this particular equation. Okay, this one is not something that you need to memorize basically. This one is a common sense, but of course if you don't understand why it becomes like this, then of course you can memorize this one. R naught equals to Ri plus X. Okay, length of the tube is L and the unit is in meter. The temperature of inner and outer surfaces, it starts from T1 in degrees Celsius and T2 in degrees Celsius respectively. Temperature difference, when we want to calculate for temperature difference, is delta T. It always starts from higher temperature to lower temperature. Alright, can you get that? Okay, so these particular terms, you need to know which one is which one. And how to differentiate that is by looking at the unit as well. Okay, thermal conductivity is watt per meter Kelvin, whereby heat transfer coefficient, this one is watt per meter square Kelvin. Okay. Alright, this particular slide, it shows the diagram for the piping, whereby you will have double pipe. Okay, when you have the product being cooled at the outer part of the layer, and then you have the product being heated at the inner part of the cylinder. Okay, and then we have triple tube. Triple tube is whereby the product is located in between the tubing at the center, in between of the first and the third tubing, and the first and third tubing is serves to supply steam, whereby this particular process it involved with heating of the product. Okay, and this one also known as indirect heating process. Indirect heating process because the steam or the hot water does not touching the product directly. Okay, this one again, another diagram, another picture of how the tubing is presented in the industry. This one, what are those tubing or cylinder that available in the industry for the cooling process or for heating processes. Okay, so for the next video, we are going to cover for heat transfer by conduction through cylinder.